my name is Cyberglad. I think it's easier for everybody to call me Cyberglad. And today I'll be talking about some abstract stuff that not usually makes sense. So here's a conference about technology, right? Because I'm going to talk about art mostly today. This is a painting by Kandinsky. It's called Computations. And this painting I saw when I was a kid, and when I saw this particular painting, I was like, oh, that's what I want to do with my life. I want to be an artist. I want to paint abstract stuff. But then, fast forwarding, I kind of got into programming. And then nowadays I'm like, okay, can I still be an artist and use all those skills that I've gained throughout the years? So it turns out that there's people doing abstract art with computers. One of them is Vera. The painting on the background is one of her famous paintings back in the, I don't know when, but many decades ago. Also Nies, he's also done lots of work in the computer. And Nies' work is focused on generative art, and you're probably being asking yourself, what is generative art? Because that's in my talk abstract. And I know lots of people ask me, but what is generative art? So basically, generative art is when you co-author your art with something else. It doesn't have to be necessarily a person or a computer, or it can be anything. So you have your art, you put some rules there, and then you let this third party decide what's going to be. So in the case of Nies, you can see the random bit in the middle there, which is he generated somehow. And then I thought to myself, okay, I really like this, abstract art, computers, I'm going to do this. So, okay, let's implement some of Nies' works. So the first thing I do, like everybody else, is Google it. And then I Google it, like, how to create art with programming. And literally the first thing that came up was 3 videos. And then I saw this first video, how to draw with code. And then I thought to myself, that is exactly what I want to do. Then I clicked the video, and at some point I learned, oh, I need to learn processing, because that's what everybody's using to create art on the computer. So I tried it, and I tried to recreate Nies' work with this mesh triangulation. And as you can see, this is the code, the processing code to generate this. And this is not readable at all, not only because it's extremely small in this slide, but also because it's lots of code that you have to write in order to get it done. So let's break into pieces. I'm a functional programmer. I like my algebraic data types. So I have a mesh, which is basically 3 triangles, and I have the coordinates for them in the 2D plane, and another integer just to say, oh, now disturb this position in some way. So then I create my data types, and basically what I want to do is, based on the size of my canvas, I get the height and the width, and I generate a random list of numbers. And then I create the mesh. I add the disturbance, where the points are going to move, and then I triangulate everything, and then I draw. And the cool thing about it that I interact with the real world. with these functions. One that I look up the environment, the size of my canvas, and another one that I actually draw stuff. So you think to yourself, oh, that is cool, that is super cool. I can finally understand how to do a triangular mesh. But the sad thing is that the language I just showed you, it does not exist. So what are we gonna do now? Basically, we're gonna build it. So a few things to know from doing generative art. First is that you should always be careful, because in order for this code to work, it has to be exactly this way. If you change the background to the draw function or method, you're probably gonna see nothing, because it's not gonna work anymore, because it's gonna repaint every time, and you thought, oh, I just broke my code, and you did. But actually, it's just a line that is in the wrong position. Also, it's super slow sometimes. Maybe I'm a bad programmer, but I have problems with this sometimes. So this is a video capture. It's generating particles. It may not strike to you as a really slow simulation, but it is because I had to make this GIF really, really fast because I was really bored by it. But you can see that it kind of flakes a bit in the middle of the thing. So it can get really slow sometimes. And the most important, art code is bad and unmaintainable. For instance, this, I have no idea what this is doing. It would probably take me a day to find out what it's doing here and possibly fix it. So I would probably just start over. So now we get to the point, okay, what do we need to have like a programming language to do generative art? So first, pure functions, because I'm a functional programmer. I like pure functions. I like to save the configurations of my canvas to be able to ask it, oh, what is the size, without having to hard code whatever size. I also want to be able to talk to one of this third party. That could be anything, but I want to talk to them, and they have to be non-deterministic. Otherwise, it's just some creative piece of code that I'm just gonna run. And also, I want to output cool art. That's what I really want at the end. And maybe somehow have it optimized so I don't have to wait forever to have it done. So in summary, I need basically to perform 3 actions. I need to draw to a canvas. I need to generate random values. And I need to look up values from a context. So let's start with the first one that I'm calling the canvas effect. I need an operation that I call draw and an initial state that is blank. So if we analyze how this is going to work, with the blank, if I have the first piece and the second piece is a blank, if I merge them, I have the star, same for the blank one in a different position. And if I merge two, I have the final piece with 2 parts. And I can also associate them differently. So I can merge first the 2 and later the second, or the late 2 and then the first. So by this, I can say that the canvas effect is a monoid, because it has the neutral element blank, and the draw merges images, and the draw is also associative. But now talking about the other two, they're kind of boring because they don't do much. For instance, I don't care the order when I'm reading stuff from the context. The same for random numbers. I don't care, I just want random numbers. But at least they are commutative, so I know something about those two effects. So you probably think now, oh, great, you just are saying some algebraic things about those effects, but what is that about? Why do I need to care about this? So it turns out I can automatically parallelize it. But you also think, but wait, what is parallelism? What do you mean when you say that? You're saying something related to concurrency, maybe? No, I'm talking about evaluation strategy. Basically, if I have a function and I apply 3 arguments to it, I can evaluate each of these 3 arguments in parallel and then apply the function. Or I could also do it sequentially, as all the language does. So when I have those commutative actions, I can basically run them all in parallel. And when I have more other actions, I can parallel fold them, meaning I have a tree, and then I can associatively merge them together in parallel. Okay, cool. We made good progress now. We can make stuff parallel, but you're probably asking yourself, oh, okay, the big problem with your code, with generative art code, is that lookups, right? That's why you want to parallelize them. So it turns out that we can do more. What I've been calling actions, you can think of them as effects, and as effects, you can think of them as monads. Cool. You know I was going to drop the M-bomb at some point, right? So, but the thing about monads is that we kind of need to wait for the last computation to run for us to proceed. So how are we gonna parallelize them? So they're not really much fun for us to make it automatic. But we have, it's not really known of cousin applicatives. They're really good for parallelism because they're just like the regular functions that I just showed you, but inside a context. So now you probably ask yourself, nice, we can talk about applicatives and all this Haskell stuff, but how can we possibly exploit parallelism from this? Because they're different things. But it turns out we can ask a little help from category theory to help us find a way. So it turns out that both applicatives and monads are monoidal categories. So instead of having my effects as monads or as applicatives, I can have my effects as monoids. And then I can create this sort of a free monoid, if everybody is familiar with free monads. I can create this free monoid where I can have this big tree where I can put both applicatives and monads. So I have this T here, which is the binary operator that the monoids ask for. So basically, what I need to do is to create these 2 data types. One, there is functional compositions, and when we put that, we get a monad out of the free monoid. But if we put a deconvolution, we get an applicative. I know you're probably scared now about this deconvolution, but you just let it be. You really don't need to read lots of base papers to understand what deconvolution is. But it's basically the same types as we have for the applicative and monad operators, but now as a data type. So the cool thing about it is that I can go back and forth from them, but because there is a left and a right adjoint that I can go back and forth in category theory, but you also don't need to bother yourself about this. The only thing you have to know about this is that we can always do this. Sometimes the applicative effect and the monadic effect, they are not exact the same thing. So if you try to go back and forth with them, you're probably going to have problems. But we can, for the same effect, we can go back and forth. Meaning, now we can schedule our parallelism better, because we can choose, oh, now I'm going to go sequential, because it's better for our performance, or I want to run this in parallel. There's also a bonus that I'm not going to talk about, but arrows are also a monoidal category, so you can also have arrow effects together with this, but it's for another day. Another bonus point is that we can statically analyze applicatives, meaning that, for instance, if I'm getting back a value from the context, sometimes I can analyze it and say, oh, I'm reading too much the size of the canvas. Maybe I can save this value somewhere else to make it easier. So you can optimize statically applicatives, but you cannot do this with monads. So you're thinking, oh, great, this is all great, and I really want to try it out. So I have a repository, but you will have to know Haskell for that, sorry, and probably some extensions, JHC extensions, also sorry. But the cool thing is that now you can generate code. You have a setup record where you put your values, and then you have this iterate function where you can pass coordinates to iterate. This is a random walk. So I'm walking 20 units of space that I don't remember what it is, but you're walking and then you're drawing and then you're choosing each of the 8 directions you can go, and it's randomly choosing which directions you go. And every time I go to one of this direction, I draw a line and 2 circles, and then I return the last coordinate. So here I can parallelize the drawing phase. And also a cool thing I did about this is that I also made the styles an effect, meaning that you can change the behavior of the style, meaning that you can draw a line and then get in the middle and then make the line a circle or whatever you want and change the color, etc. So here, now the biggest takeaways from this talk is that algebraic effects are cool. You didn't know, but I've just taught you algebraic effects. Now you can go to ICFP and hang out with your academic colleagues. that also the category theory may be useful after all. We can use it to do something that will actually improve our lives, not just make our Twitter looks nicer. And also that you can always look for associativity and commutativity when trying to parallelize stuff, because then you can either full parallel them or you can change the order by running in independent order. And the last bit, which for me is the most important, is that you can use science money to fund art projects. Yeah, because I'm a PhD student in computer science, so I'm actually doing art, but nobody in my university needs to know that. So another bonus point is that generative art programs are allomorphisms for the category theorists among us. It means that I have this my cohort, which is an image that goes to an image, meaning that I will start with probably a blank canvas, and at the end I will also have a canvas with my art. So during the process, I'm probably going to generate lots of values, unfolding them, and then after lots of computations, I'm going to fold them back again to have our finalized art. And the good thing about it, there is some literature on how to parallelize allomorphisms, so we can also exploit that, which is the next step of my research. That's it, thank you.
So, does anyone have any questions?
Hopefully, because we've got enough time until then.
Yes.
That was a lovely talk.
What
made you think of using this specifically for art? Are there any other uses that you think would seem fit for it?
Oh, probably useful stuff you can do with this. But I like art better.
Oh, okay. Is it like a personal thing? Good idea.
Yeah, just could you please show this GitHub link again? Because
Sure. Maybe. I don't remember. But I mean, you probably don't want to try it because I'm rewriting it for like the 10th time. So you probably want to check it out like in December. Sorry? Hopefully this or next year.
yeah, so as far as artists go, who you think could be automated, any other artists? For example, Mondrian and some others that come to mind?
Yeah, I mean, if you want to create like a random Mondrian, you can totally do it. I think I started doing this, but it's not finished. Yeah, you can pretty much do Mondrian and then have like the squares in different places. But I think the trickiest bit is going to create like rules to work with the colors. I think it's the trickiest part of it, not the squares themselves.
Any more? We've got plenty of time.
I just looked on Twitter and saw one of your pinned tweets was an artwork that you'd produced, but it'd be great if you could share some more of the stuff that you've actually produced.
Ooh. Oops. So, oh, cool. So when I was trying to generate the triangular mesh, I got the algorithm wrong, so that was what I got of there. And then this, and then this, and this, and then I finally got it right. So I also have other variations on.
Is that the code mesh logo?
Wow, it can be. And also I have this, which is exact the same code from this one, but changing the styles. So you can basically change your art by basically changing the styles. That you're going to change the handlers, but I'm not supposed to talk about handlers. But yeah.
Another 15 minutes if you want to.
Okay, so basically when you have algebraic effects, you have the operations, and then they are abstract in a sense that you have to have a handler to actually make stuff. So you can just have one effect that is, for instance, a state, and then you can create different handlers for it that access memory or whatever that you have, I/O, kids of Haskell, or and other data types. So in this case, I have the styles here. The canonical handler is the one that behaves as you would expect, like I have a circle, it draws a circle, but then I create another handler that kind of rewrites it, and then I have this instead of another line rather than a circle. So that's how I do it, and then at the end I compose all the handlers to get something like this.
One of the things about processing, I think, that makes it very popular with people who are not programmers is it has a whole environment and stuff, and it's just a shame that the actual language that people have to work with is this sort of horrible imperative thing. A few years ago, there was an attempt to sort of keep processing but replace it with a more functionally flavored language, in that case based on Scala. It's kind of that's a bit rotted. It's very old. But have you thought about maybe doing something like that with maybe I mean maybe someone could build something using Eta, so another JVM language but a functional one, and somehow or other try and sort of slip that into the processing environment and make something more interesting for people to work with.
Okay, I'm going to tell you a secret, because this I'm presenting to you is going to be an actual language, and I'm going to compile it to WebAssembly to run on the browser. But you don't know that because it's a bit far from then.
December of next year.
Oh, many Decembers.
That was really cool, thank you. It's really nice to see more art programming done in functional languages. Most of the stuff I see tends to be done in processing or uses the Web Canvas API or something like that, which means it always compiles to JavaScript. So PureScript I've seen used a bunch. Since you're using Haskell, I was wondering how you actually plotting, once you've built the description of your image, how are you actually rendering it?
Cairo.
Sorry?
Cairo.
Okay.
Yeah, I just have lots of bindings for Cairo and C. Sorry.
Any more questions?
So all the work you produce are all digital. Have you ever thought about turning it into actually material, like a
Yeah,
canvas?
there is a paper that was published this year, and there is another paper that is gonna come out in beginning of next year, which goes through this in detail. So we can talk later, and then I can point you to that.
Anyone else? We've still got time. No? Okay, cool. Thank you very much.